Hello ladies and gentlemen, thanks for tuning in today for this lecture, which is going to be lecture 8 of GGS 300 Quantitative Methods for Spatial Science. Today we're going to be focusing on inferential statistics and hypothesis testing. So before we begin, I just want to say well done on the midterm exam. Those scores look pretty good overall, so I was really happy actually. I hope now you've all handed in assignment 5, which was due on the 16th of October. Assignment 6 will be set this week. It's actually already up on Blackboard now, and that's going to also be due on the following Friday, which is now October 23rd. So please make sure that you reach out to me if you have any problems with that work, if you have any questions that you want me to help answer. Okay, so what are we doing today? Well, as I've already stated, we're going to be introducing inferential statistics, and we're going to be building on particularly some of those things that we've done in the last couple of classes. So descriptive statistics seems like a long time ago now, but particularly the probability part and the sampling part that we've done the last couple of lectures, that's going to be pretty important for how we move ahead now and we start to do hypothesis testing. And we're going to be building over the next couple of lectures, essentially to be covering a range of different inferential statistics tests that you'll all be able to apply in your own research, and that's a really great thing to be able to do. You know, it makes you highly employable. The best jobs out there are going to be quantitative jobs that require you to do at least some coding. So I think that this is, a really key part of your toolbox in terms of how you progress over the coming years. So I hope you enjoy the content. In the second lecture, I covered the scientific research process. So particularly how we use quantitative information within spatial science. And for most of what we've done so far, we've covered mainly what's on the left-hand side of the screen here. So that's particularly where we might collect data and we might process the descriptive statistics and draw some conclusions from that. And slowly we've been progressing more to the right-hand side of the slide here. So particularly where we might formulate hypotheses, go out and collect some sample data, test those hypotheses, evaluate them, and then we're able to either gain real impact from the decisions that we've reached. So we're able to make the world a better place, essentially. Or we're able to go back and refine the model or develop new theory, which has an important academic role. Although that bit is theoretical still, it's still very important to how we gain impact, because quite often you might reach the end of a research process and realize that you need to go out and do some more research. I mean, that's generally, unfortunately, what happens. But that's important because you've learned something. And particularly as we move into the later classes, I'll probably emphasize many times that no result is still a result, and that's important. And that's always useful to know, perhaps if there was a finding that you've been unable to reproduce in the academic literature, and there is an increasing value placed on those replication studies. Okay, so let's not get too sidetracked. We're going to focus more on these inferential statistical tests today. Let's start with hypothesis testing. So we've covered what a hypothesis is in the previous classes. So this is essentially a statement that needs to be either verified or shown to be false. And we do hypothesis testing using sample statistics. So when we sample, we try to get a point estimate given some confidence interval. We try to estimate that point from a subset of data for the overall population. That's the basis of what we've been doing in the sampling over the last couple of classes. And we're able to use sample statistics to determine if we have enough evidence to suggest a given hypothesis is true, or whether we don't have enough evidence to reject the null hypothesis. So the classical hypothesis testing approach has 6 steps to either accept or reject the hypothesis based on a certain level of significance that we may set. So hypothesis testing is binary. We either the hypothesis is either true or false. So when we state hypotheses, a hypothesis against the null hypothesis, they are complementary. So this is true or false. And the level of significance is arbitrarily set depending on the discipline, which I've covered before, but which is really important because maybe not so much in spatial science, but if you work in medical science, then the significance level is essential, because if you're going to administer a medical treatment to someone that you think might actually have some sort of disease, and there's some sort of downside to that medical treatment, it could cost money, it could also potentially cause negative health effects on the individual. You need to be absolutely confident that they need that treatment, and therefore you might set a much more stringent significance level so that you're far more confident that course of action is needed. So thankfully, we won't have to deal with questions perhaps as arduous as that in spatial science, and we'll cover that today. So essentially, normally we have a significance level of about 5%, so 0.05, so that we can be 95% confident in the result that we obtain. And that's fairly standard. You'll see that throughout pretty much all of the academic literature in this area. But as we move towards regression tables in the later classes, I'll show you some examples of how those statistics are presented in those examples, and actually you will indicate how results are significant to different levels using particular notation types. So I don't want to get bogged down with that for now, but that's something that I will present at a later date. So this 6-step process, essentially step 1, we need to state the null and the alternative hypothesis. So these are complements. Step 2, we need to select the appropriate statistical test. And we're going to talk about issues with selecting the appropriate statistical test later in this class, and also so later in this lecture, and also in the book. In the chapter that you read this week, there's also a couple of pages on issues associated with making these decisions, and it's going to be absolutely essential that you understand some of these issues for when you do, for example, your dissertation research, because you need to demonstrate that the statistical tests that you've applied have met the required assumptions for that statistical test. Otherwise, you just produce junk results, and that's obviously not what you want. Okay, step 3, we need to set the level of significance. Step 4, we then need to delineate the regions of rejection and non-rejection of the null hypothesis within the distribution that we're working with. And when we do that, you should remember, it should be familiar to you, given what we covered in the previous weeks, how we delineate those types of regions. Then we need to calculate the test statistics. So this is the lecture. We're going to be going over some kind of theoretical high-level concepts such as this. Qualitatively, I'll be explaining these steps, and quantitatively, I'll give you the math so you understand how we calculate these specific statistics. But in the lab after this lecture, we will be going over the manual way to calculate these statistics line by line in the code base in R, which is a great thing to know. And then we're also going to be using a package to calculate those test statistics. And then hopefully you go from kind of qualitative understanding, theoretical math understanding, through to manually calculating these test statistics in the code, through to using a package where it just basically does it all for you. And the reason why we're doing that is because we all use packages. So we use packages to run statistical tests, and that's fine once you know what the package is doing. But at this stage, we need to make sure that you understand how to calculate these statistics manually, so that you have a decent understanding of what the code's doing behind the scenes. Finally, then we need to make a decision regarding the null hypothesis in the final step. Okay, so that's the 6 steps, and we're going to go over those now, and we're going to talk a little bit about what we do at each one of those steps. So in step 1, we need to state the null and the alternative hypothesis. So we state here that the null hypothesis is H0. So this is a statistical hypothesis to be tested. And we would expect that under the null hypothesis that the sample mean is essentially the same as the population mean, so that there's no difference between the sample that we've achieved from the total population. The alternative hypothesis is the hypothesis that is contrary to the null hypothesis. And within this, if it's non-directional, as we state here, then we would just expect that the sample mean that we have is not equal to the population mean. So for the alternate hypothesis you see here, this is indicating that the population mean is not equal to the sample mean here. So there's some sort of effect that's going on, which indicates that the value that we get is either larger or smaller than the population value. And we're not saying whether it's going to be larger or smaller in this particular hypothesis. We're just merely saying that there is some sort of effect, and it could be either higher or lower. So given that statement that I've just made about the alternative hypothesis, we are also able to make directional alternative hypotheses. So for example, here when I say directional, what we mean is that we think that the sample mean that we have is either larger or smaller than the population mean. So for example, if I said that I think the house prices in Fairfax City are larger than elsewhere in Virginia State, across the state of Virginia, then that would be a directional one-sided alternate hypothesis because I'm saying that I expect them to be larger than the population mean. Okay? So that would be this HA version here. You could also say that you expect the house prices in Virginia to be lower than elsewhere in the state, and that would be a directional one-sided hypothesis here. But you'd be looking at a different part of the distribution. You'd be looking at the lower end rather than the top end. Okay, so they're just high-level examples, but we'll get to those within the course material today. So as I stated up here, for the alternate hypothesis, we could have a non-directional two-sided alternative hypothesis. So we've already covered this. So this is just basically where we don't say whether we think it's larger or smaller. The reason why this matters is that we need to change some of the quantitative metrics for our alpha value, and then how we think about that within the rest of the distribution based on where we expect that result to be. Okay. So within all of these tests, we are essentially looking at whether or not we think the null is true. And the null hypothesis is always that we expect there to be no difference between the sample that we have and the total population. And I've just provided you with a little snippet for that example, which I've already discussed down here. So the null hypothesis for the house price example that I gave you is that essentially there would be no difference between the house prices in Fairfax City and the rest of Virginia. But if we were using a non-directional two-sided alternate hypothesis in this case, then essentially we would state that there is a significant difference between the house prices in Fairfax City and Virginia. Okay, so in that case we don't state whether they're higher or lower, we just say there's a difference. Okay, so that was step one. Now let's get to step two, which is selecting the appropriate statistical test. And this is actually quite challenging, because what I found when I first learned stats was that you kind of have to know all of the different assumptions involved in the different tests. And there's a lot of background knowledge to try and get there. So I kind of struggled with this at first. Now in retrospect, it's kind of easier because I feel like I have more of an understanding of the different types of data and the key assumptions involved in different statistical tests, and therefore you kind of know that someone can just describe to you the problem and you get a feel for what is the right test to use essentially. But I think at your stage, this is going to be one of the more challenging things to work out, and that's because there's a lot of background knowledge that goes into choosing the right test, basically. So basically, the test, it depends on the type of question that you're asking and whether the assumptions are met. So today we're going to focus on just two. So that's the one sample difference of means test and the one sample difference of proportions test. And they're both covered in the book. So we're going to be giving you an overview of what those tests do now, and then you'll have the opportunity to read about those tests in greater depth within McGrew et al. Okay, step 3, we need to select the level of significance that we're going to use. So the significance level is the alpha value, which we've covered previously, and the common values are 0.05 or 0.1. So you'll come across these in many cases. So respectively, that's saying that you either have a 95% or a 90% level of confidence in the result that you obtain. The significance level is also known as the likelihood to commit a type 1 error. So what's a type 1 error? Well, basically this is a false positive, okay? And that's opposed to a type 2 error, which is a false negative. You need to learn these and understand the difference between these different terms, and that's because firstly it's important to your statistical understanding, but also you're going to be tested on these, so you can be definitely sure there's going to be these types of questions within future quizzes or exams. So make sure that you understand that a type 1 error occurs when we reject the null hypothesis, but the null hypothesis is actually true. And a type 2 error occurs when we do not reject the null hypothesis, but the null hypothesis is actually false. So make sure that you learn what these mean, write it down, learn it rote, watch other videos on YouTube if you still need to get some understanding around this. But I'll provide the slides, and you can have a look at these types of tables. They're pretty common, basically, to help you understand the different outcomes that you could get. So based on the reality of you having a null hypothesis and an alternative hypothesis, you would have two outcomes where you get the accurate right result, and then you would have two outcomes potentially which are the wrong result, either a type 1 error or a type 2 error. And this is important. So step 4, we need to delineate the areas of rejection and non-rejection within the distributional space that we're going to have. So the area of rejection can be thought of in two different ways, and that is depending on whether we have a non-directional approach. So that's where we don't say whether we think the effect is going to be higher or lower than the population mean. Or we could have a one-tailed effect, which is directional. So maybe we think in advance that the house prices in Fairfax are going to be larger than the house prices across the state of Virginia. Okay, the critical value, Z or T, separates the rejection and the non-rejection zones. So one-tailed, we need to find the Z value associated with alpha, and two-tailed, we find the Z value associated with alpha divided by 2, because the error is split into both tails. Okay, so I hope that's clear. I just have some graphical extracts here that allow you to understand what would happen in a two-tailed non-directional format. So that's case 1, or a one-tailed directional format, that's case 2. So in case 1, we're interested in, we're not saying whether we think that the house prices are higher or lower, and therefore the sample mean that we might get could be could be either in this tail at the top or here in the bottom part of the tail. You'll remember these lower and upper bounds that we've also specified in previous lectures, because we did it, for example, when we were sampling and we wanted to provide a confidence estimate. But essentially, if the mean that we obtain falls above, for example, this upper bound here, then we would reject the null hypothesis, and we would accept the alternative hypothesis. Okay, so for example, with an alpha of 0.05, we would have a bound here which is 95% of the values, and basically this upper and lower bound would be 1.96 standard deviations above the mean at this point here, or it would be 1.96 standard deviations below the mean at this point down here. So that's for where we have a non-directional specification. If we have a directional specification, then we're basically saying that we think the house prices in Fairfax are higher than those in the rest of the state of Virginia. And we would have a different boundary, essentially, for the point at which we would reject the null hypothesis. Okay. So then we need to calculate the test statistic, and that depends on the test that you're using. So we're going to cover a couple of these today, and then we're going to be getting into progressively more complex tests, you could say, as we move through the end of the course, particularly as we get to regression, which is, is a step above in terms of how you understand the statistical techniques that we're going over, but it's also incredibly powerful. And go look at regression. It's used in every academic department in the world, most likely in a quantitative subject, because it's a very powerful statistical technique. Okay, so we're going to use sample statistics today to calculate test statistics, and the test statistics are often based on Z or T values, but not always. But these should be familiar to you because we covered them in the previous lectures. So you can use a T value if you've got a smaller sample than you would ideally want, or you can use a Z value if you have a large enough sample. And then finally, once we've been through this whole process, we need to make a decision regarding the null hypothesis. So if the calculated test statistic falls in the area of the null hypothesis rejection, then we need to reject the null hypothesis with a level of confidence which is equal to 1 minus the alpha value. So I've specifically stated what you should write here when you are writing a report using these techniques, and that's because the wording is very specific. You need to make sure that you're using a wording which reflects what you are and aren't able to say given the test that you use. So in this circumstance, we would say that we reject the null hypothesis of house prices being the same in the same in Fairfax as they are in the rest of Virginia state. And we're doing that with 95% confidence and conclude that the alternative hypothesis, oh, sorry, I got that wrong. Let's just go back to the H0 and the HA values that I used at the start of this, which is that we reject the null hypothesis of the house prices in Fairfax being the same as in Virginia state with 95% confidence. And therefore we conclude that the alternative hypothesis of house prices in Fairfax being larger or smaller than in Virginia state, so significantly different, is true, essentially. So that's long-winded. I think it complicates it because I'm trying to give you the specific null hypothesis and the alternative hypothesis within that statement. But what's important here is that we say we reject the null hypothesis with a 95% confidence, and therefore we conclude that the alternative hypothesis is true. Okay, so that's the really important part. And then looking at another outcome, given that these are complements, if the calculated test statistic does not fall into the area of rejection, then we fail to reject the null hypothesis. And then I've specifically stated how you should state that here. So we fail to reject the null hypothesis. There is insufficient evidence to show that the null hypothesis of house prices in house prices in Fairfax being different. There is insufficient evidence to show the null hypothesis of house prices in Virginia being significantly, sort of in Fairfax, significantly different from Virginia, is false at the 95% confidence level. So I don't want to confuse it too much, but these are the types of statements that you need to make sure that you're reporting when you're writing your results within a piece of analysis, but then also the conclusion, because that's where you're going to state what your ultimate finding was. And the reason why it's important to state it in those ways is that the reality is that most academics aren't going to sit down and read an entire paper unless it's directly related to their area, or unless they're actually asked to review that piece of work. The reality is that most people are going to look at the abstract. If the abstract's interesting, then they're going to look at the conclusions. If the conclusions are interesting, they're going to look at the results tables and any graphics that are included in the paper. And rarely, I think, will actually anyone read the full piece. So this is why it's so important that you report this information in this way, and that it gets filtered through into the conclusion and the abstract for the academic paper that you're writing. Okay, so I hope that that's clear. Perhaps I didn't word some of these as well as I would have liked, but I think the point retains that you've got these statements, you know how to use them, and we're going to be covering these within the lecture today, but also in the chapter that you have to read this week, and also in the lab. So hopefully by the time we've gone through all of that, this starts to become a lot more clear. So the key point is that, in other words, given these statements, if the calculated statistic is larger in magnitude than the critical value which we're selecting, we reject the null hypothesis. Okay, and the important thing to remember is that the null hypothesis is never proven as true, because it's just accepted as the norm already. And I will get into this later when we cover issues in hypothesis testing and significance testing. Okay, so essentially this statement here about the calculated statistic being larger in magnitude than the critical value, let's just go back to case 1 that we covered already. We've specified our rejection intervals. Imagine that for the 95% confidence level, so an alpha value of 0.05, we would need the test statistic to be above 1.65 standard deviations above the mean, or below the mean, depending on which way the effect goes. And as a consequence, if we had Z here and it was 1.89 standard deviations above the mean, then that essentially means that we would reject the null hypothesis. Okay. So hopefully that's clear, and let's do some examples now. So let's focus on just one sample test. So these are essentially some of the easiest tests, because we're just taking a sample and we're getting a single number, and we're just going to crank out the calculations based on the math which I'm going to present, and that's going to give us some test statistics to evaluate. So one sample test, as I said, we assume that we take a single sample. We want to compare the sample statistic to a population parameter to determine if it's similar or different. Often we assume some sort of the population parameter using past studies or logic. So for example, if we use a census, that might show that the mean household size is 2.61 nationally. Then the question is the average for Middletown significantly different? And we might go out, we might collect data and compare it to that existing population parameter. So that's just giving you a bit of flavour of the types of examples that you might get in the book. We'll go back to Ed's favourite example, which is house prices in Fairfax in Virginia. To do that type of analysis, you can just get the population mean value for house prices from Zillow, for example, for the whole of Virginia, which is $296,604. And then we could go out and we could sample houses within the city of Fairfax and develop a sample and then test whether this sample that we've got is significantly different from this population mean for house prices across the rest of the state. So let's calculate a particular example. I'm going to start by showing you some of the math. So to do the one sample difference in means tests, it means we need to compare the sample mean to the population mean. There are statistical assumptions and requirements that we need to meet in order to use this approach. So the sample has to be randomly sampled. We have to assume that the population has a normal distribution. You'll remember that the central limit theorem that we covered in the previous class. And that's a tricky one in reality, because often the population might not be normally distributed. So you might have to go out and undertake a variety of transformations for your own sample data, for example, in order to obtain a normally distributed set of data points. And then finally, we need to assume that this is interval or ratio data. And we're able to set the hypothesized mean here. So essentially this is the null hypothesis. We're able to set the null hypothesis, which is why mu, which is the population mean, is equal to the sample mean, so the hypothesized mean. And then the alternate hypothesis is that they are significantly different. So the population mean is not equal to the mean of the sample, essentially. This is based on a non-directional approach. Or we could say that it has a particular direction, depending on what we thought, as we've already covered in this part of the lecture. The test statistic is either Z or T, depending on the sample size. What's important is that we are able to calculate the Z or the T depending on basically subtracting the population mean from the sample mean and then dividing it by the standard error. So we calculated the standard error last week. So essentially it's the standard deviation divided by the square root of the number of samples that we have. Okay, so that's the math. Let's do it for a particular example. So an energy official claims that the oil output per well in the United States has declined from the 1998 level of 11.1 barrels per day. 50 wells are randomly sampled by this energy official throughout the US, and the mean output within that sample is 10.7 barrels per day. Okay? The standard deviation is 1.3 barrels. Now I want you to test this claim using an alpha value of 0.1, so 0.1 level of significance. So what we're going to do first is we're going to identify the null hypothesis and the alternative hypothesis. So the null hypothesis is that the sample mean matches the population mean, essentially. And then the alternative hypothesis is that the sample mean is less than the previous population mean. In step 2, we're going to, as a consequence, define the fact we're going to use a one-tailed, one-sample difference of means using Z. So it's one-tailed because we've said here that, or the energy official has said that the oil output is falling, so it's declined. So we're looking to see whether that sample value is lower than the previous population value that we have, which is why it's one-tailed. So that's step 2. Step 3, we've already defined that we want to use an alpha value of 0.1 level of significance. And then we need to define the Z critical value. Okay, so this is going to be this lower bound here, the point where we specify the do not reject and the reject zone within the distribution. So how do we get that value? Well, you remember that we can enter these values using Q norm into R, and it will just produce the Z score for that particular portion of the distribution. So if we enter 0.1 alpha into Q norm, then we get a Z score critical value of minus 1.28. So this is 1.28 standard deviations below the mean. That's the value at this particular line where the mouse is currently. So that's delineating the do not reject region from the reject region. So that's setting up all of the different values that we have. Now let's do the number crunching. So if we just go back, you'll remember that we need to subtract the population mean from the sample mean. So that's what we're doing here for the numerator. And then the denominator, we need to get the standard error of the mean. So it's the standard deviation divided by the square root of the sample size. So it's 1.3 divided by the square root of 50. And then when we actually do that calculation, we get minus 2.18 as the z-score. So firstly, if you're still not clear on how to calculate that, take those numbers, tap them into a spreadsheet or use a calculator and just generate that statistic so you know how it's being done. So that's my first point. Second point, if we get a z-score of minus 2.18, then we know it's lower than the threshold value that we previously set. And as a consequence, we're able now to reject the null hypothesis at 90% confidence. Okay, so that's an example of how we run through this particular test and how we get the values that we need, and we lead to a conclusion where we're able to, in this circumstance, actually reject the null hypothesis at the 90% confidence level. And this is the type of logic which you're going to need to show when you go through the lab in the next session, but then also when you carry out the homework and potentially also write about this in the exam. Great. So that was for mean values, so one sample difference of means. Now we're going to focus on one sample difference of proportions test. It's quite similar, it's just that, you know, instead of using a mean point value, we're using a proportional value. So this compares a sample proportion to a population proportion. It has slightly different requirements, so you have to randomly sample. You're assuming that random sampling has taken place, but then you would also expect that the variable is binary in this particular instance. So we have our null hypothesis and our alternative hypothesis set up. So for the null hypothesis, we expect that the proportion in the sample is essentially the same as the proportion in the population, whereas the alternative hypothesis is that the proportion in the sample isn't equal to the proportion in the population, if we were choosing a non-directional approach. The test statistic is the z-score, and we're able to calculate this using this equation here. And essentially, this time round, we have the standard error of the proportion, which forms the denominator. So you have the formula here in order to calculate the z-score value for this particular test. Let's go through an example. So Middletown officials want to know if the proportion of families with one or more children under 18 is different from the national trend. A random sample is compiled of 250 Middletown families. 105, and that's 0.42, of the families had children under age 18. The last census shows that 48.6% of families have children under 18. The question is Middletown smaller than the national trend based on this metric? So what we need to do is we need to state the null hypothesis first, which is that there's no difference, so the proportion is the same as the national trend. And then we state the alternative hypothesis, which is that the proportion, in this case, is lower than the national trend. As a consequence of it being expected to be lower, we're using a one-tailed, one-sample difference of proportions using z-score. We know that the alpha value, so the level of significance which we're setting, which is 0.1. The critical z value based on this, which is the same as before, but you can obtain, for example, either looking in a z table, or you can standardize z table, or you can go into R and type this into Q norm and get the value of interest. And then essentially we can tap the numbers into the math equation which we presented in the previous slide. Okay, and when we do that, we end up with this value minus 2.12 is the z value, which is below the critical threshold score, which means that we can reject the null at 90% confidence. Okay, so I hope for both of those examples that's relatively well understood by you. So I think that we've got the math, we've got the 6 different steps each time. We're able from the question to define the hypotheses, the type of test we're using, the alpha and the critical score values, and then we're able to use those equations to calculate the z-score. And then once we've done that, we're able to make reach a decision for how we either for how we approach for the statement, the concluding statement that we make essentially, which is about whether or not we reject the null hypothesis, or whether we don't have enough information to reject the null hypothesis. So let me just finish on the issues associated with these tests. So there are a few. The p-value, the probability value. So in hypothesis testing, we're comparing hypotheses to an arbitrary alpha value. This is actually very controversial in scientific research, and that's because this is all classical statistics. So a lot of these tests, you know, the way that we formulate this, it was all developed almost a century ago. Thinking has moved on quite a bit since then, and some people don't like classical statistics at all, as it turns out, for a variety of reasons, often related to the p-value. And you might have heard of Bayesian statistics, but there are a growing number of research scientists who have ditched this type of inferential classical statistical approach for a Bayesian approach. Now, I don't want to get too much into detail here, but I just want to make you aware that p-values are often misinterpreted, and there's quite a lot of academic literature which has been published in very high-ranked and reputable journals, which essentially identifies some of the key issues that we have with p-values. In many cases, they just completely rubbish the whole concept. But I will dig those papers out for you and share them with you so you can get more of a deeper understanding. But it is important for you to just be aware of these issues. Okay. And I think also just one thing that I want to emphasize, is that the probability of a type 1 error occurring is equal to the alpha value, the p value. And often this is arbitrarily set, as I've already said. Okay, so let's move on. By using the p-value, you can essentially skip parts or all of the classical hypothesis testing procedure. Okay, yeah, so we've been over quite a bit of this already today, but the point is that if you don't understand hypothesis testing, then p-values won't be very easy for you. So today we've gone over some of the basics, because you need to do that before you can move to the more complicated ways in which we generate statistics. So one question is, well, how does the p-value testing actually work? Well, if you have a p-value, a smaller p-value indicates that the observed statistic is essentially further away from the null hypothesis. Okay, and as we move towards regression, this is going to be something which you really need to have a decent grasp on. So, for example, the p-value of 0.5 indicates of 0.05 indicates if the null hypothesis was actually true, there is a 5% chance of drawing the samples being tested. So basically, we've got a 5% chance that we randomly got a sample that's said to reject the null hypothesis, when in reality is that you shouldn't have rejected it. So I think this is one of the key points that I want to make to you. We say with 95% confidence that we can reject the null hypothesis, but that still means that there's a 5% chance that the results just randomly occurred. So if there's anything that I want you to take from these couple of slides, it's a recognition that just because you're rejecting the null hypothesis, that's just one finding, and there's still an element that result could just have occurred by chance. And generally, what you need for something to be conclusive in the academic literature is a wide body of research which is suggesting that something is true. It's good to write a paper where you find an interesting result, but there needs to be a much larger and more weighty amount of evidence for something to be kind of widely accepted. We've just worked recently on an econometric piece looking at firm creation, so the number of new firms that are started, essentially, and we looked at what happened in relation to the rollout of superfast broadband. And the kind of existing thinking is that if you roll out superfast broadband, new firms are more likely to be started, essentially. And that's because they've got access to the internet. There's new digital economy firms that are able to provide new services from having faster broadband. That's kind of the prevailing thought in the area. But in reality, after going through many iterations of the econometric model, we found that the rate of firm creation actually was starting to decline over time, even after superfast broadband had been rolled out, so faster broadband. And this goes against the prevailing thought in the area, which is, very interesting. But I think just because we've published a paper saying this, it would take many more papers for there to be kind of a body of work which people would start to accept. And I think one of the issues is, you've got this element of randomness in the model, in the data that you've collected, but also, there's an element of how you specify the model, which, I don't want to get into here, but although we display this as kind of quantitative hard scientific research, and I definitely believe that's a great thing, that there is a bit of an art in how you specify the model based on the existing theory, and that can lead to different results. So anyway, I don't want to get too bogged down by this now, but p-values are, incredibly important, but there's still an element of potential random occurrence, even if you have a sample which suggests that there's a significant difference from the population. So how do we use p-values? Well, we compare the p-value to the hypothesized alpha value. So for example, we conduct a test intending to reject the null hypothesis, and when you get a p-value of less than 0.1. But you can also use p-values to make more kind of qualitative choices. Yeah, okay, fine. I mean, it could still influence your analysis even if it's not significant, but you wouldn't be able to say with certainty that an effect was present. It might influence how you redesign future studies and do more sampling, but you really need to be careful about your scientific process here. So one-tail testing, p-value is the probability of getting the calculated stat or more extreme, and the two-tail testing, the p-value is double the probability of getting the value or more extreme. Okay, because we're accounting for both tails. So the issues with this, well, firstly, I need to state that the null hypothesis is always a statement relating to established thought. So in the example I gave earlier, this is basically that by delivering high-speed broadband, you get more firms being started, essentially, okay? So that's that there's nothing new or significant occurring. H alpha is challenging the assertion, or it's a new point of view, hence why you're doing research into it. What's important though is that the way you formulate the null hypothesis and the alternative hypothesis it needs to be done a priori. Okay, so this is a big complicated Latin word that I don't want to bog you down with, but it's how it's termed in the literature, and you may read papers where you come across it. All this means is that you establish it based on theory, empirical knowledge prior to doing the piece of research. So it's your existing understanding of the world, your existing knowledge. And the reason why this is so important is partly an academic integrity issue. You need to set your hypotheses out in advance, and then you need to go out and collect data based on those hypotheses you've already stated. What you must not do is run your analysis, look at what was significant in the results, and then write your analysis up based on the hypothesis. So this is called fishing. It's a very bad academic practice. It's the type of practice which, if you were found out doing, you could potentially lose your job. You would definitely lose academic credibility. And remember that being a good spatial scientist is entirely dependent on your research integrity. So you need to make sure that you specify these hypotheses in advance, and then you go out and you get data to test those hypotheses. You can't go from the data results back to the hypotheses to change them, okay? So that's issue one. Issue two is challenging to work out whether you should be making a one-sided or a two-sided hypothesis. And it depends on the framework, and I'm afraid there are no hard and fast rules. So all you're learning in this lecture essentially is just the quantitative framework that allows you to carry out statistical analysis, and therefore there's certain judgment calls within that analysis that you're going to have to make as a researcher based on what is right in the context, for example. So I am not able to make these decisions for you. And often, even when you're very experienced, you can make those decisions, write up a paper, and then someone can publish another paper refuting those results because you've made certain decisions which potentially are wrong. And that's all part of the academic process, essentially. But I appreciate it's challenging. You're going to need to make a decision which way you think, what type of hypothesis you're going to have, potentially based on existing theory. So this is one reason why a really thorough literature review before you carry out your piece of research is incredibly important. Okay, so you need to read existing studies, look at existing theory, look at existing empirics, and make a judgment about how you think the world works. Okay. Issue 3, using a hypothesis test. So we always need to report the probability value, the p-value, for the hypothesis test. And I mentioned this before, that you have to be very careful with how you word your conclusions from that analysis that you carried out. So you need to consistently say that there is a strong, moderate, weak, or no evidence against the null hypothesis, depending on the body of evidence that you found. What you shouldn't say is that you accept the null hypothesis, because that's already existing status quo. So think of, in the criminal justice system, we say that people are not guilty rather than innocent. Based on the evidence that you have here, they might not be guilty, essentially. You can't say for certainty that they are innocent. So this is important for you to recognize. Make sure when you think of this class and you think of the things that you took away, you need to remember a couple of key things. One of them is that there's very specific ways to word the conclusions that you reach, and that if you need to do a statistical analysis and you need to write up those results, you can always come back to these lecture slides and take the way that they were phrased within this class and just insert them into your context based on the results that you found, and then you know that you're going to be on strong ground, essentially, for the way that you report your results, not make any mistakes. One of the fourth issues that we have is the number of degrees of freedom, and this will become more and more important as we move towards the tests, which we're going to cover later in the lecture, later in the classes this term. So let's just recap on what the degrees of freedom actually are. So essentially, you earn a degree of freedom when you collect each data value. You spend a degree of freedom to estimate each statistical parameter. So for example, if you're estimating journey to work, you collect 51 data points, so the journey to work time. You then need to calculate the sample mean for inferential testing of the mean. Then the number of degrees of freedom is going to be 51 minus 1. Okay, so you get 50 degrees of freedom. Why is that? Well, actually, the way that I understood it when I learned statistics, which I'm going to tell you about now, is that imagine you are allocating football players into positions on a team on the field. And essentially, each player that you place could go to any of the other positions. So the first one could go to any position. The second one could go to any of the other positions that aren't already filled. As you go through allocating each of those players, every player has an option of going to more than one position until you get to the last one. The last player to be allocated has to go to the one position that is not yet filled, okay? And that's why the number of degrees of freedom are the sample size minus 1. Okay, so I hope that that's a good way for you to understand it. You're allocating, let's just say it's a soccer team, you're allocating 11 positions on the field of play. So you've got one goalkeeper and 10 players who are actually out in the field. You're going to allocate the 10 players first. You can have a striker, you can have a defender. You go through all of those 10 players. And then finally, you allocate the goalkeeper. And because the goalkeeper can't go to any other position on the field because you've already filled them all, that goalkeeper doesn't have any degrees of freedom to move, just has to go to that one position. So I hope that that's clear. This is going to become a more important issue as we move through to the future tests. Issue 5. This is actually a hard one. This is what I found really hard when I was first trying to estimate statistical models. I was never really that confident about whether what I was doing should have been a parametric or a non-parametric test. I didn't really know which one I should have been selecting, so it's important to discuss this. So parametric is based on the normal distribution, non-parametric based on data that aren't normally distributed, essentially. So we've talked about parametric tests so far. We assume that they're normally distributed. What about those populations that aren't normally distributed? Well, essentially, non-parametric tests, also known as distribution-free, do not require interval ratio data or parameters. Okay, so this is something which we're going to be dealing with in the future. Couple of lectures, and a good example is, maybe you go out and you do a survey and you're dealing with categorical data. That may mean, as a consequence, therefore, that you have to use a non-parametric test. And there's a variety of different strategies for how you select these. So here's some rules which you can follow. So as I already said, if your data are nominal or ordinal, then you have to run an appropriate non-parametric test. You can test the distribution of a quantitative variable, for example, to see if it's normally distributed or if it's significantly different from that. And if it is significantly different from the normal distribution, then you'll have to use a non-parametric test. So this is something that we can get to later, and it's slightly more sophisticated because you're kind of using a test in advance to select the right test that you then use. But the nice thing about that is you've got a quantitative metric which justifies your selection of your test. So that's very nice. So I hope that wasn't too confusing for you, because we covered a lot of ground. I hope I didn't confuse the hypothesis statement step too much, but if I have, then you've got the book to go through and to read that, and you've got the lecture slides as well, so you know specifically how you should be wording those conclusions based on what you've found, and based on the confidence that you have in that result based on your alpha value. So today, this was the lecture. We've now got the lab next, and then there will be a quiz which I will set on this. And then hopefully you'll be well set up for how we're going to progress in the next couple of weeks, which is more moving towards those types of statistical tests that you will use in your own research as you move towards doing a dissertation, for example, or your own academic papers. Great, so thank you very much for tuning in today to Lecture 8 on GGS 300, and let me know if you have any queries or questions about the content. I'll see you in the lab. Thank you.